are now. I see there's 41 people attending, but more people will come on as we go. Ryan, do you want to show my face or, oh, sorry, do I turn on my camera? Yeah, hold on. Okay. So welcome everyone. My name is Mark O'Malley. I'm the Chief Scientist for the Energy System Integration Group. Charlie Smith is the Executive Director of ESIG. Sometimes refers to me as the Chief Leprechaun in his usual manner. And he thought that Midsummer's Night, which it is this evening, was the appropriate time for the Leprechaun to host one of these events. So with all joking apart, so Charlie Smith and myself are in ESIG, and part of the role that we have is that we are also heavily involved in the Global Power System Transformation Consortium, which is 6 system operators from around the world who are all facing very high penetrations of renewables. And pillar 1 of the G-PST is run by ESIG. And it's really looking at how to get very quickly to very high penetrations of renewables and address all the research issues that are there. They're largely speaking to do with inverter-based resources and control rooms, etc. This evening's talk has come about because of the research agenda, and I'll be passing it on to Priya Dante from Carnegie Mellon University very shortly. So this is a joint ESIG G-PST webinar series. This evening we've got another one actually next week with Shahil Shah of NREL, and there's also other seminar series going on within G-PST to do with the other pillars. The other pillars have to do with education, modeling, etc., etc. There's other pillars involved in G-PST. There's also other seminars going on inside the ESIG webinar series as well. So webinars, webinars, webinars. So without further ado, I'm going to pass it over to Priya Dante of Carnegie Mellon University, who can introduce ourselves. But one thing to say, questions for this will all be done through slido.com. So slido.com, and then the code, so to speak, is ESIG21, ESIG21. Okay, so I'm going to pass this over to Priya. Priya?
All right, thanks, Mark. So yeah, thanks everyone for joining today. I'm very excited to have a conversation about the ways in which AI can potentially play a role in power system transformation. It's going to be moderated by me. I am Priya Dante. I'm a PhD student at Carnegie Mellon and also one of the co-founders and chairs of Climate Change AI. And not joining us today, but very much involved in putting this together, was also Kyrie Baker, who is an assistant professor at CU Boulder and also leading EPRI's, the Electric Power Research Institute, EPRI's AI and Power Grand Challenge on Environmental Impacts. So diving in, today's webinar builds on a webinar that the 4 organizations, G-PST, ESIG, Climate Change AI, and EPRI co-hosted in March, where we basically sat down with the 6 system operators represented within G-PST and asked for their impressions of the different ways in which they're facing issues with respect to needing to transform their control systems, their forecasting systems, their planning systems in order to contend with power system transformation, and also get their perspectives on how AI can potentially play a role in that. So while that webinar basically got the system operators' perspectives on these issues, building on that, today's webinar will basically dive into, from the research side, how maybe we see both AI and power systems research communities plugging into actually addressing these challenges posed by the system operators. And so today we will hear from 2 speakers, one of whom is Baosen Zhang, and the other one is Ferdinando Fioretto. Each of them will give a 5-minute intro presentation, after which we'll have some amount of moderated Q&A that builds explicitly upon some of the points raised in the last webinar. For those who were not at the last webinar, don't worry about it. We'll give enough context so that you can still follow the discussion this time around. And then we'll have some time for open Q&A from the audience. And again, we'll be taking these questions through Slido. Slido.com, code is ESIG21, and we'll also post a link to that in the chat. So before kind of handing it over to our speakers, I just want to briefly mention that in addition to G-PST and ESIG, this webinar is co-organized by EPRI and Climate Change AI. In particular, EPRI recently launched a series of 5 grand challenges during its AI and Electric Power Summit, where the goal is to bring together stakeholders from a wide variety of sectors in order to tackle various grand challenges within the electric power sector. And in particular, one of these challenges is the AI's environmental impacts challenge, which tries to look at how AI can basically foster power system transformation in more sustainable directions, and thinking about also AI's own impact on sustainability directions. So in a moment, I'll also put the link to the AI Environmental Impacts Grand Challenge mailing list in the chat, and this is again led by Kyrie Baker. And this is also co-organized by Climate Change AI, which is a nonprofit initiative to catalyze impactful work at the intersection of climate change and AI by providing a network, resources, funding, events, and so forth. And so you can check out our various reports, educational resources, join our workshop series or webinars or happy hours, and also check out various funding opportunities that are on our website. And again, I'll post a link to the newsletter in the chat. So with that, I want to introduce our first speaker. So our first speaker will be Dr. Ferdinando Fioretto, who is an assistant professor in the Electrical Engineering and Computer Science Department at Syracuse University. His research focuses on machine learning, optimization, privacy, and fairness, particularly thinking about how to integrate optimization and machine learning for solving complex decision problems with applications to energy systems, and more broadly also how to make AI algorithms better aligned with societal values, especially privacy and fairness. Dr. Fioretto is a recipient of the 2022 NSF Career Award, various other early career awards, dissertation awards, and best paper awards, including 2 IEEE Transactions on Power Systems best paper awards. So Nando, take it away, and thanks for presenting.
Thank you, Priya, for the nice introduction. So I'll be sharing my screen. Perfect. I trust you see my screen now. So yes, I am Ferdinando Fioretto. I am a computer scientist. I have a strong interest in machine learning and AI, as well as data privacy, and have an interest, a passion also about power system and their application. So part of my work has been focusing on how to use machine learning and AI to solve complex optimization problems, especially in the context of critical engineering systems, including the power network, gas networks, and supply chain systems. And so deep learning seems to be particularly suitable to learn to approximate solutions to these hard optimization problems that are arising in such type of applications, because it can capture nonlinearities, and we can exploit the learned representations to deliver very fast approximations of the original problems. But one of the key issues that we've been facing is essentially the presence of hard constraints and the physical laws that those systems carry with them. And so this should be taken into account during the predictions. And this is also the central focus of one of my research area. And so to be a little bit more precise, what we typically want to do is, so we have a learning task which has takes input some data which describes the problem and its associated solutions, and we want to learn some parametric approximation of this original minimizer. And so we do that by the means of training a neural network, and which ideally solves constraint empirical minimization problem. And really the challenge that we're facing is in letting this network to output prediction that satisfies such constraints. And so one of the solutions that my group has proposed was of integrating discrete and continuous optimization and learning. So one solution exploits Lagrangian duality, for example, to where the learning task is continuously augmented with constraints violations that we're experiencing during the training, so that we learn to produce not only a strong approximator of the solutions, but also learning to satisfy the underlying constraints of the problem. And so we have applied this framework to a variety of applications and problems, in particular solving COPF problems back in late 2019 was shown to give us very strong results. And we have a series of subsequent work which addressed also scalability as well extension to security constraints of PFs. And so we were able to obtain very high fidelity models at very fast computational runtime. So all this was really, really exciting. And we also went over and started looking at why those systems seems to work. So why we can learn such type of good approximations. And here, this is actually research that we're still currently doing. I don't think we completely understand this, but an interesting aspect is that it seems that trajectories that are output by generators in COPF outputs, for example, can be nicely approximated with some degree with the piecewise linear functions, and ReLU neural networks are known to represent well piecewise linear functions. Obviously, in very high dimensions, the problem becomes much more difficult, but we were able to characterize the error associated with classes of functions that can be learned by a ReLU network for a model with fixed capacity. There's some degree of interest in the statement here, because in a sense, what seems to happen is that as the model capability essentially expands, then you should be able to learn more and more complex piecewise linear function, but this actually does not seem to arise. So for example, in this plot here, I'm showing that we extend the size of the model, but the accuracy of the task that we're learning does not necessarily become better. And this is whenever we're trying to just match the solution without the constraints. And so we also try to understand why those effects are arising, and we found a notable connection within essentially the space, the inner representation of the neural network, that when we are not imposing constraints does not learn to characterize the connection between power generations and voltage variables and so on, while when we are also augmenting the learning process to learn constraints, then we can automatically also characterize such type of components and thus learn much better solutions. Just very briefly, my other area of work is in data privacy. So we need essentially a huge amount of data typically to train those models, and sometimes this data cannot even be released. So my other research efforts have been in developing privacy preserving mechanisms that allow us to release power system data, which gives probably privacy guarantees, but also ensures to retain very high, similar solution with respect to the original optimization problems when such problems are executed on this private data. So I'm going to stop here.
All right, thanks so much, Nando, for the intro to your work, which I think will be very relevant as we go on in the rest of this discussion as well. So I now want to introduce our second speaker, who is Dr. Baosen Zhang, who is the Keith and Nancy Endowed Career Development Professor in Electrical and Computer Engineering at the University of Washington. His research focuses on control, optimization, and learning applied to power systems and other cyber-physical systems. He's previously been at a variety of awesome institutions, University of Toronto, UC Berkeley, Stanford. He received the NSF Career Award, as well as several Best Paper Awards as well. So Baosen, take it away.
All right, thanks, Freya, for the introduction. Thanks, guys, for inviting me here. So let me share my screen. Okay, all right, yeah, so as Freya said, I've been the UW for about 7 years. And my group sort of work on a bunch of different topics within power and energy systems. So spanning from OPF to forecasting to control and learning. So in here, I'll tell you a little bit about some of the AI-related stuff we have done. So one of the first things we did in this space is scenario generation. So as we plan for the grid of the future, or as we plan for sort of larger penetration of renewables, one thing is we want to generate sort of plausible scenarios of different, let's say, wind or solar. So one place where deep learning or AI has played an important role is to make this process much, much easier. So using something called a GAN, we can reliably generate essentially a very large amount of data. And interestingly, so we can build on top of this. We can do sort of conditional forecasting. We can look at what will happen if we do something in the grid or we observe some things. And this has been applied by Seattle City Light in their planning problems. And so next, quickly going through the topics. Next one is, in addition to generating data, we also want to control some systems. So you can imagine that, let's say we want to control a building, right? So this shows a picture of our own building, our ECE building. For large buildings, it's well known that there are a lot of thermal storage within large buildings. So by controlling the temperature set points within the buildings, we can significantly reduce the power consumption. So the tricky part is, how do we get a model of the building, right? And adding sensors to building is simple. But it turns out we use our standard deep neural network to learn this to model this kind of buildings. It's not a very nice control problem. So it turns out the right way to use data and use neural networks is to constrain the neural network. So here we develop something called input convex neural networks. And when you put this as models into a control problem, you get convex optimization problems, which are much easier to solve. And another big benefit is then allows you to do theory, right? So we're going beyond just black boxes now. We can provide theoretical guarantees. And so unlike Mark, who wants to do very big things, so all this has been applied very close to home. So we now use this on our campus to control our buildings. And the last thing is, I want to touch on is design for control of inverters. So we have inverters. These are power electronic devices. And they can implement a lot of different control laws, where they're not constrained really to be what synchronous machines are. So there's quite a bit of design freedom in designing their response to, let's say, how they should do frequency control. And in this case, but when you have this kind of flexibility, you sort of don't know what the right structure is. And if you just use, again, standard deep learning algorithm, turns out sometimes you design controller is actually not stable for a system. So again, the theme is we should constrain the neural networks enough, find the right structure on the neural network. So here it turns out to be something called the monotone structure, where we can sort of, again, provide proof-fully guarantee stability and performance while doing a lot better than traditional linear controller designs. And this has been tried in sort of lab setups, and we're hoping to scale this more. So with that, I'll stop to give us more time for questions and answers, and look forward to that.
All right, thanks, Baosen. And again, sort of spanning the forecasting, optimization, and control spectrum there, which again, we'll touch on a lot of themes that we're going to talk about today. Yeah, so having heard those great introductions from both Baosen and Nando, we're now going to sort of start a kind of moderated Q&A portion of this, where building on last time's discussion, we've sort of generated a couple of different questions to try to dive into the various kinds of considerations that were shared during last time's webinar. During this time, those in the audience, please do drop questions into Slido, as we will sort of get to those in the second half of this webinar as well. So before we dive into the specific questions from last time, I wanted to ask one higher level question to both of you, Baosen and Nando, which is, in some sense, why are we talking about AI and machine learning in the first place? What value proposition do these tools provide for forecasting, operations, control, and planning that maybe existing tools do not? And maybe are there even cases where maybe these are not the right tools, where we should not be thinking about them? So either of you, feel free to jump in.
I guess I'll start.
Yeah, you can go first.
Yeah, I'll take a first crack at this. But I think, right, so I think right now is a good time to look at this kind of problems. If you ask me, let's say 15 years ago, will we need AI and learning? Maybe not, right? I think right now, the reason now is a good time to do this is, one, we have a lot more things going on in the system. We have renewables. Along with renewables, we have a lot more controllable devices. So doing everything from a first principle modeling perspective has become very challenging. If you look at, let's say, 20, 30 years ago, we have a pretty good understanding of the system and all the methods work. So there's not much room for improvement. Whereas now there's quite a bit of room for improvement. There's actually quite a bit of room, just to keep the grid running. We need some new methods. So, one thing I guess following up on sort of the thing I talked about is for building control, right? So building, we can squeeze a lot of juice out of them. But developing a first order sort of PDE, partial differential equation model of building is very, very time consuming. Takes years to do. Whereas putting sensors in buildings is very cheap, and we can learn from the sensors, right? So that gives us a much easier way of modeling and controlling our system. I guess the key is to do it, in the right way, or in the way that is compatible with other operations in the system.
Yeah, I just a few points maybe to add. So on the why, I think in my perspective, one of the main characteristic, right, that we have been exploiting in current deep learners is speed. I mean, this is not only for operational purposes, but also if you think about it in terms of if they can be exploited in other forms, such as in plannings. So being able to approximate, for example, ACOPF precisely at almost negligible run times will allow us to make longitudinal planning study using much more high fidelity models than what is typically adopted. Also, I think that there is a huge opportunity in the current trend of combining learning and optimization, because this might be able to give us a tool where we can understand which predictions matter the most for achieving some desired objective. So I don't know if I think at an example, maybe training in an end-to-end models where inputs are forecast and outputs are decision, then we can start asking which part of the model, right? Which part of the maybe timeframes of the forecast needs to be improved so that we can potentially achieve better decisions. And so I don't think this was, previously achievable with the technology that we had. In terms of limitations, I mean, this is a good question, because I think that until a few years ago, it was not even clear that we were able to handle hard domain knowledge, physics, and constraints in ML predictors, while now this seems to start to be the norm. And so I think that this is a rapidly evolving reality. So maybe what we think it's a current limitation today might not be tomorrow. But I would say that my group currently struggle in developing, ML technology that is suitable for very high dimensional discrete problems. So maybe this is really, the challenge out there. Maybe we're not going to be able to achieve that. And we do have optimizer that in the end we should take advances from. But on the other hand, ML-based approaches have also been successful in deriving heuristics for search algorithms, branch and cut methods. So, accelerating other frameworks which are typically adopted in the resolution of very discrete problems in a sense.
Yeah, thank you both for sharing those perspectives. So to summarize, it seems like basically we're seeing a lot more complexity and sort of need for a mix in some sense between physics-based and more black box methods, as we don't necessarily understand the full situational awareness of the underlying system. And correspondingly, in some sense, we sort of need a hybridization of methods as well, where there are many ways in which AI and machine learning methods can play well with existing optimization and control methods to maybe provide that correct combination of capabilities. So thank you for sharing that. So I want to dive into now the specific questions from the G-PST research agenda that we heard about last time from the system operators. So I want to start with, for those who know the agenda very well, question number 27, which is on forecasting. So last time we heard from AEMO about their use of, probabilistic graphical models and decision trees for probabilistic forecasting, as they, increasingly need to forecast the performance of heterogeneous sources, renewables, including behind the meter resources. And they also need to start to disaggregate the forecast errors associated with different types of sources in order to understand, again, like how that affects their decision making on the system. They also mentioned that in many cases, they actually tend to use linear models due to a need for transparency and interpretability. So given that sort of summary of what they discussed last time, the first question I want to ask on this forecasting side, or this probabilistic forecasting side, is, are there any particular new directions in AI that you're excited about to maybe address this direction of probabilistic forecasting?
I guess, yeah, so I can still take this one first. Yeah, so I think forecasting is actually, I think, one of the most promising and the area where I've seen AI being used the most, right? So I think, yeah, so I think using AI or deep neural networks, things like that, think models beyond linear models, we can do a lot better job at forecasting a lot more realistic scenarios. For example, GAN is a much better tool, in my opinion, in forecasting scenarios than linear models. It's much easier to work with, much easier to train, can generate, especially for high dimensional data, when you have sort of spatial and temporal correlation, there's sort of adversarial networks can generate much more realistic data. I think for transparency, and we also run into this when we're working with City Light, our own utility, is a lot of time they don't want sort of just data coming at them. They want to do this sort of conditioning. Right? So if we do this, what happens then? If we do that, what happens then? That kind of question, when GAN sort of first came out, was hard to answer. They're sort of considered to be too black box, things out. But nowadays, I think the technology, especially in the learning front, has moved beyond that. We're actually putting a lot of very sort of reasonable and very sort of very understandable conditions into the boxes and ask them to generate different scenarios. So I think that's the area where I see a lot of work for AI.
Yes, I think I have a much more limited knowledge about forecasting models, but I do think that one of the challenge it's probably the absence of current methods in providing confidence interval in predictions, tolerance to noise in the data and measurements. So how do they translate into effects in the outputs, especially when you have this highly nonlinear models? On the other hand, we have also seen advances in adversarial machine learning, and thus we might be able to leverage solutions that are typically adopted there in robust ML. In terms of explainability, I go back and forth on this point because I agree. I read the questions, and there are different definitions of explainability. Each seems to agree on one particular part of explainability, and sometimes it's very related with reliability. The term of explainability. What I think, what I tend to see commonly is that I think that system operators have an enormous background knowledge on the system that they are operating daily, and they have gained this ability to learn how to respond to some daily challenges. So they know what to breaker to operate, how to change topology, one node to split, and so on. And so in response to that, I think that they expect there is a certain change in the system. And so if we are able to construct predictors tools that rely on sort of modeling techniques, forecasting, but also integrated with predictions that are reflecting those expectations of the operators, then I think that this is a way to essentially balance this explainability component. And if we're able to entrust this ability of the AI system to kind of match the expectation of the operators, I think that then we would be in a better position of not constantly asking the ML essentially of the AI system to provide explanations, because typically a human does not always have to provide explanations when we have that trust.
Yeah, no, it's a really great point about, exactly, the distinction between trust and explainability, and which is the thing that we are actually going for ultimately. One might be a means to the end, but it might not be the only means to that particular end. Before we move on to the next question, Baosen, is there anything you wanted to sort of add before we do that?
Yeah, so I think trust is an interesting issue. I think that's probably one big area for us to look at, right? So how do we establish trust? Not beyond forecasting or scenario generation, but also I think going back to a high level question is, where do we see AI starts to have struggles? As a lot of times when you interface with customers, then learning tend not to do so well when you have humans. At least for the energy system, we have humans in the loops and learning to not do so well. There's a trust issue, there are privacy issues. I think that's Nanos as a big area for us to focus on.
Awesome. Yeah, thank you. So moving on to the next G-PST research question we covered last time, again, number 12 for those following along. This is on control. So last time we heard from EnergyNet about, a really big shift in the way that they view power system control. In particular, as grids are starting to operate under a wider range of operating conditions and with the introduction of renewables, we're also seeing, a move from traditional generator-driven systems where publicly the physical parameters of the system to moving to, fast reacting power electronic converters where we don't necessarily always know the parameters. So EnergyNet sort of argued that given this, we likely need to move from, maybe slow to run physics-based modeling approaches that are currently used to maybe faster to run black box AI models that can help identify the state of the system in a data-driven way and extract hidden features and actually employ that in order to control the system. So the question here, maybe the first one is, as we brainstormed during last time's Q&A, even if we start to use black box AI approaches, there is still a need to ensure the safety and robustness of these approaches. And there's also an audience question similarly asking about, how do you ensure feasibility with AI solutions? And as you both have hinted at, this maybe implies a potential for hybrid approaches that combine elements of black box AI with traditional physical modeling. And so I wanted to ask, kind of in that sort of hybrid AI and physical modeling space, are there any particular methodological directions that you're excited about and feel like could be pushed along these lines? Maybe let's start with Nando this time.
Yeah, good question. I think, this is there seems to be room for work in physics-informed neural network in this particular space where we want to extract some parameters, of the system dynamics, essentially of the system. But in terms of robustness, I think that there was a connection with distribution shifts, right? And this was the question that was arising last time. What I see here is the need of tools for assessing the issues of possible distribution, shift in power system application, because you're right, the robustness to distribution shift is critical for deploying essentially the solution, this machine learning model. But to my knowledge, there's been little work in defining the underlying mechanisms that cause those shifts. And so there's not so much understanding in my knowledge on when and why those models generalize, especially under realistic settings. And thus, we should ask whether can we define distribution shift to be robust, and how do we audit the model to distribution shift? So this seems to call for also research in fundamental AI question, right? And I think that it has been argued that like data augmentation techniques may help in various contexts. It has been argued that when data augmentation promotes invariance, then you should exploit it, and that when you have generative models Baosen was discussing earlier, when you have these generative models that can learn to approximate the true conditional distribution, it should be the same for training and test data. If you can capture that, then you can augment the data, the training data, with that generative model, so to correct for the distribution shift. But yeah, so I think that really this calls for more test set, more experiments, and really try to understand and characterize when such distribution shifts are arising, but in this domain really in particular.
Yeah, absolutely. And before I hand it over to Baosen to further comment, just to comment on one of the things that Nando was talking about. So yeah, exactly. During last time's Q&A, there was a question about, the fact that the data fed into AI and machine learning models isn't always representative of the scenarios that the model actually acts on. And so this is what is called in the machine learning community distribution shift. And I just wanted to define that because, of course, the word distribution is a bit overloaded in a power systems context. But by distribution shift, it is this question of basically when you have a machine learning model that's trained in one scenario, how well can it adapt to a different scenario? And so this is also related to the question that somebody asked in the Q&A about, how can AI and machine learning extrapolate to future scenarios? So with that, Baosen, I'll throw it over to you, thinking about, in the context of control, do you have any comments on like hybrid physical modeling approaches or approaches for dealing with distribution shift that you're particularly excited about?
Sure. Yeah. Great. Yeah. So I'll sort of give a focus on a narrow topic about inverters. I think a lot of questions on Q&A about that, so I should knock them out at this time. So for inverters, though, think about, let's say, designing, say, frequency control for inverter. So this basically saying that you have inverters, instead of doing droop, you can do something else, right? So given frequency deviation, how should you change your active power set point? And so of course, it can be linear. So a lot of work has been trying to say, how do we sort of reproduce the synchronous machines? How do we make them look like synchronous machines? But we can ask them, can we go beyond that, right? And the easiest way, at least, to do this is to parameterize the controller using neural networks. This is very easy to do. But the bad thing, I guess, also the good thing about neural networks is they can be anything. So once you say they can be anything, there's nothing you can hope to show. Right? There's nothing you can say about the system if you allow them to be anything. So it turns out the right way, I guess, is to again use physics. Right? We have a power system. We know the power flow in the system. We know there are voltages, currents, and so on. But we also don't want to constrain the neural networks or the inverters too much. So we want to find the right class of controllers, control functions, where the system remains stable. And turns out this question is actually not very new to the AI part, because you can ask a similar, basic question is to say, how do I know a power system with linear droop control law is stable? How do I know this system is stable? And turns out you do this if you have you find a Lyapunov function and show this Lyapunov function shows stability. And that Lyapunov function works beyond linear controllers. So it works for a wide class of functions. So now this gives us a way to constrain the neural networks we have on the inverters, right? So they have to be, so in this case, it turns out to be, they just need to be monotone functions. We spend some effort designing how a neural network can be constrained monotone. That's also very easy to do. Once you have this, the system is stable. We'll do no worse than linear functions in terms of stability. So we're now making stability worse. We can make performance better. We can learn what these shapes are. Sometimes you end up with very weird shapes that I have no idea how to design by hand. But that's where machine learning is, so black box learning is useful. But on the other hand, we constrain the tools. It turns out we can still provide guarantees. I think what I'm excited is finding the right constraints on the tools we use. Right? We want to leverage their capability, but also find the right constraints. I think this is also much easier for power systems than for some generic computer science problems. We have relatively simple equations to write down, and we can develop this kind of condition, where for other domains, it's probably much harder.
Yeah, absolutely. And some of my work explores this as well, which is exciting. Basically, how can you bring in formulations from optimization control, electrical engineering, and basically use those to provide almost like a safety gate around the black box portion of your neural network model. And of course, this requires very deep collaboration between the machine learning community and those who are formulating the power systems constraints in order to co-design these methods to make sure both sides of that work very well. So yeah, absolutely agreed. Before we turn it over to the audience questions, I want to dive into this last G-PST research agenda question from last time, so 37, which was about planning. So last time we heard from National Grid ESO about the different stages of their planning process, which involve first developing scenarios and modeling techniques, then developing network solutions based on those scenarios, then assessing those solutions using network modeling and optimization techniques. They also mentioned that in addition to, build solutions where you actually introduce something new to the power grid, they also need to assess the role of non-build solutions that can provide flexibility. So things like storage and demand response. And AI was proposed as being able to plug in maybe across this planning process. So doing things like helping to identify network solutions and investment paths by combining heuristic-based approaches and optimization-based techniques, and also modeling some of these non-build flexibility-based solutions in order to understand what kinds of capacity and flexibility they can actually provide to the grid. So on that line of things, on this planning side, are there any particular new directions in AI that you're excited about to address these challenges? And then also, since this is an area that I believe both of you have worked in, there's actually been a fair amount of work using AI and machine learning for ACOPF and unit commitment. So maybe optimization problems in operations contexts in order to speed up the solution time of those models. Do you think any of those methods are actually applicable to the planning side of things as well? So maybe this time let's start with, Nando again.
Yeah, so absolutely. I think this is a great question. So I'm a believer that the solution that they have been developed for essentially speed up the optimization processes that are arising in power systems, ACOPF, security constrained OPFs, can be readily adopted for planning purposes. Once the computations become cheap, then we can simulate a large number of scenarios. And once we have an objective defined in mind, then once that becomes cheap to assess, so we can actually, I think we can readily use those tools for assessing much larger, much longer longitudinal study in such conditions. And once again, like I was mentioning this earlier, I think that the combination, once we also start combining as learning and optimization approaches, right, and they start becoming differentiable so that we can start reasoning about the inputs, then we can start also trying to understand what type of conditions of the inputs we should change so that we are more able to achieve a desired output, right? And so this becomes very much like a design problem, like an inverse problem. So this is a very exciting area.
Awesome. Baosen, anything you want to add?
Yes, I agree. This is a very exciting area. I think planning is also an area where AI can sort of make a lot of contributions today, actually, without waiting for new technology. So, I mean, personal experiences, right? We did a lot of scenario generation. And actually for planning is what we do is we generate a bunch of scenarios. Then because we could not solve these sort of long time horizon optimization problem, we had to throw out most of the scenarios. Then we solve for a few scenarios, which is a little bit anticlimactic, I guess. So the idea is, can we just, quickly run through all the scenarios, right? I think where Nando and Freya and Carrie, you guys work also along this area is how do you solve OPF very, very fast? And I think that's a benefit in planning is because you look at operations, then replacing, let's say, ACOPF solver by machine learning based solver is still challenging. You have to think about constraints, right? What if your input and output data are, what if your training and testing data are different? Can we guarantee constraint satisfaction? All of those are still challenging. So I think, there's some sense of, I guess we're trying to replace what operators are currently use. I think that's a high bar to cross. Whereas in planning, a lot of planning models doesn't even have DCOPF. You have this sort of, approximate DCOPF for a lot of constraints that just not look at because you want to solve the optimization problems, right? So even there, even LPs, linear programming are very hard to solve from using straight, the current optimization tools we have. But then if you can combine learning and optimization over there to look at a large number of scenarios, solving not only DCOPF, but even ACOPF, then there I think we have much sort of where the technologies are more successful, right? Because there then probabilistic guarantees make sense, right? You don't have to be right for every scenario, just be right for most of them. And then there we're not trying to replace the tools, but you can actually add a lot to what the current planning solution. So I think that's a great area to look at.
Awesome. Yeah, thank you both for sharing those perspectives, and also Baosen, thanks for the shout out to our work as well. So, gonna go over to the audience questions here, and in the interest of time, what I'm gonna do is I'll read a question and probably ask one of you in particular to answer it. The other one, feel free to jump in if you want to add, but in the interest of time, we'll try to get through as many as possible. So the first one, which I'll direct to Nando, is Nando, you had made the point about system trust maybe being the more important metric than explainability, and sort of Mark O'Malley asks, I suspect system operators will be conservative about adopting AI unless there is explainability. Do you agree or disagree with that?
Yeah, again, I think there's a certain degree of explainability that we have to provide. But there's also, my point before was that we are lacking a fundamental agreement on what explainability means. And sometimes in my conversation with stakeholders, I found that, trust is really what they mean by explainability. And so in a sense, one of the things that I found recurrently is that is this dependency by what one suspects the system to do once an action is performed and what the AI would do otherwise. And yeah, this seems to be very recurrent in many different, in a variety of applications. So I do agree with that point. I simply think that we need, very, very, very precise definition of explainability in order to tackle it well.
Yeah, absolutely. Thanks for sharing that. Okay, so Baosen, what is your opinion on using, physics-informed neural networks for inverse problems, things like identifying parameters from data?
Right, yeah, so I think that's an interesting area. I haven't done too much in that area, so Nando, feel free to add to my response. But I think that's a new perspective on state estimation. Right? In some sense, we're trying to do state estimation. We have some states we're trying to estimate them. But state estimation runs into, it's hard to do for nonlinear systems. We don't quite know how to do it well. So I think physics-informed neural networks give us another way to do parameter differentiation, give us another way to sort of build algorithms in that area. And especially as more inverters, more devices coming, we don't want to necessarily identify every parameter in the system. But we want to identify their sort of equivalent or aggregate systems. Then I think this core physics-informed approaches will be very useful there.
Yeah, just to, since you call my name, I do agree. I mean, this is a super promising and exciting area. I think one of the challenge that might arise in that area is like in any other problem in ML is dimensionality. So once you're inverting, some task in a very high dimension, then the amount of data essentially that you need to provide might need to grow substantially. And so that's that process of even generating data smartly. This is what we typically do in a physics-informed neural network. We sample from some random distributions. But if we're able to generate data smartly, then this might actually aid the process to better learn, both forward and backward, essentially.
Yeah, definitely agreed. So we have a lot of questions about control, so I'm going to attempt to sort of cluster them and let both of you comment as you would like on those. So some of these questions basically have to do with what it means to guarantee stability when you think about a machine learning context. So for example, Mark O'Malley asks, stability with inverter-based resources is partially to do with the interactions between the IBRs and other power electronics, for example, HVDC. Can you guarantee stability in these cases? Another person asks, how do you actually go about designing power electronics converters using AI? So what kinds of data do you need? And what kinds of specifications do you need? When we design, power electronic converters, do we tune PID controllers? Do we, construct controllers from anew? So basically a lot of questions about what does it actually mean to design a stable controller, thinking about the data, thinking about the relationship to existing methods, and thinking about also the stability specifications and the interactions with other components on the power grid.
Okay, so yeah, I'll take a first crack at this. So you're right. So the precise statement for this is something like the following. Right? Suppose the inverter operates in following fashion given by a bunch of differential equations. Suppose HVDC will operate by a bunch of differential equations. Suppose the network has this bunch of differential equations. Then the system viewed as a whole is stable in the normal sense. And this we can guarantee because there's, it's not a linear system, but there's various tools to show when nonlinear systems are stable. And the benefit here is sort of you don't really need to study the big system as a whole. That turns out to be difficult. What you do is you can ensure if each part of the system behaves in a certain way, when you connect them all together, the entire system is then stable. So this goes to passivity, for example, right? So for each inverter design, we can make sure each of the inverter behaves. You connect all them together, it's guaranteed the whole system is stable. So how might you train something like this? So the way to train something like this is you would tune this sort of in an online fashion. You don't need to pre-design everything. So right in the lab, the way we do this is we will start off with a sort of nominal PID controller. We'll start with a linear PID controller. Then we'll, based on data we collect, we'll look at the performance. We'll now start to change the shape of this PID controller. We'll sort of adapt this neural network. We'll learn this parameter of this neural network by collecting data online. So as long as you make sure the neural network you design stay within these constraints, so they still have the passivity criteria, then the system is always stable. So each of them can train individually, can operate individually, right? So this is sort of one, how we're doing this. I think a challenge, an interesting question is there are always unmodeled dynamics in the system. Right? There are always sort of things you don't model, especially for inverters. There are a lot of things we don't know are there. So how robust are those things to this sort of unmodeled dynamics? How robust are to things like plug and play coming at all the system all the time? And so this is a harder question to answer. And I think the idea here is, again, that it's not that things are hard for black box or AI methods, things are easy for linear. I think it's easier for traditional methods, say linear ones or some other ones, is because they're simple enough. You can study what happens when uncertainty arises. It turns out a lot of the sort of mathematical sort of theory behind it extend to larger space of controllers, larger space of designs. So that can be pushed along. And we can still obtain some of the robustness just with more work.
Absolutely. And before, Nando, I let you add in, I'll sort of add an additional question to this mix, which Amrit Pandey asks, and Baosen, you sort of addressed this as well, that grid control is also paramount during extreme events that don't commonly occur in reality. So you don't necessarily have a bunch of sensor data that indicates those events. So the question asks, how do we get such data for training ML models, but more broadly, also, how do we deal with this in our definitions of stability? So adding that element on, Nando, let me hand it to you.
Right, this one, yeah, so, sorry, do you want me to?
Go ahead,
I was gonna hand it to Nando additionally, but then Baosen, also feel free to jump in.
Go ahead, but yeah, go ahead, Baosen.
Okay, yeah, so I'll say that, yeah, so here, right, so that's why having guarantees is important, right? Because with this kind of guarantees typically comes in terms of if the disturbances stay within this range, then we can guarantee stability. And those ranges turns out to be fairly large, so even some rare events is there. Now, when you train the performance may or may not be very good during those rare events because you won't see it a lot during normal system operation. So the idea is to always provide at least stability for those. Then, but to target the performance, target for how quickly you can recover frequency, for example, towards for more normal events there.
So in an attempt to get away from this question, because I am the least qualified to answer it, I think that there is a point that it's often arising, within my comments, which is that of I think that as we have availability of simulators, availability of tools and libraries for optimization and control systems in classical power system operations, so we do not have those for the newer ML tools that we're developing. And so I think that generally, this need of also for creating scenarios and the exact definitions of what scenarios would need to be created might arise once we have the availability of such tools. It might arise once we have the availability of, well-curated data sets, which can be translated into benchmark tools that the community can really develop over and thrive in a sense. So I think that there are a few efforts that have started arising. There is like a learning to run power network competition and NeoRIPS since a couple of years, but it's a different aspect. I'd be very, very excited to see more of those events arising in the years.
Yeah, definitely. Okay, so there are two questions from the audience about optimization problems. So Russ Philbrick asks, can you give specific examples where DCOPF linear programming solutions have difficulty solving and how ML can do better? And I suspect the clarification will be, we're actually talking about AC often in these settings, not DC where ML is providing, but I'll let Nando and Baosen comment there too. And the other question is, thinking about different paradigms for addressing optimization, Sibi Plathodam asks, how do deep reinforcement learning agents compare with supervised learning methods when you think about optimization problems? So let me start this one with Nando, sort of thinking about this, machine learning for optimization direction.
Yeah, so I think so for the first question, I think if you think at let's think at the ACOPF. So that's a nonlinear problem, and you also have difficulty typically scaling with size. So that is one of the main challenge that you have. So ML will never perform better than a solver that actually solves that problem up to a certain level of tolerance. But it might perform faster. It might, depending on what is your optimization that you have in mind. What is the function that you have in mind? If it is sole accuracy and you don't care about computational runtime, then probably ML might not be comparable in this quality assessment here. But if runtime is thrown into the equation, then ML might perform much better in the sense that it might be able to provide you much faster inference time. Or if there is uncertainty coming into the equation, then ML techniques very recently have been shown to be exceptionally handling those cases as well. So I would say that the question is to be posed and seen in these different angles, in these different phases. So this is also similar, for any type of optimization problem. Even a linear problem, it is large enough, it becomes unbearable for the system. Or if there is enough uncertainty, it becomes unbearable for the system. And so I see the same parallel. And the other question was
about reinforcement learning versus supervised learning.
Yeah, so this is so I mean we're dealing with very different beasts here, right? So because in a supervised settings we're providing labels, and we are able to map inputs to outputs in a sense. In a reinforcement learning we're learning policies, and thus we're typically we're sampling from distribution. So really you need to have this type of setting in mind, where when you're operating in a reinforcement learning, can you deploy a distribution over which you can sample, and then throw those samples and make sure that in expectation you have the desired goal. So in expectation you want to maximize some given utility, right? And I mean, there's a lot of technicality there. I think I'm gonna skip them, but yeah. So the main, I would say the main difference is in this purposes. But there's obviously a lot of work done in discrete optimization that leans toward reinforcement learning, and that is because I mean, you can actually learn to sample well, and then through those samples and iteratively build a solution, which in a supervised setting you might not be able to do, because you have these very discrete operations which produce zero gradients in the update step.
Yeah, Baosen, is there anything you wanted to add?
Right, yeah, just on the DCOP way. So I think for that problem, I think as Daniel was saying, in a planning context, even for a DCOP, it actually gets quite large. Right? So if you look at multiple years, especially if you want to look at sort of fine temporal horizons, then you typically get problem that's with few thousand variables, few thousand constraints. That is still challenging, at least for a personal computer. It's not that fast. It will solve it, but it'll take a while. And this so of course, it's a solution, you guaranteed optimal solution. It's a good solution. But you can maybe only look at a few scenarios. Whereas use machine learning, maybe your solution is 0.5% worse, but you can look at 1,000 times more scenarios, right? So that's a trade-off. I think it's worthwhile.
Absolutely.
And I think, yeah, so I think that's what. Yeah, that's that.
Sorry, yeah, and then to maybe channel what something Kyrie Baker also often mentions as well is that because ACOPF problems are often deemed too large scale or slow to solve in these settings, we tend to use DCOPF as a faster approximation. And the feasibility mismatch that is induced by using the DC approximation rather than the AC approximation is sometimes worse than if you use a machine learning model to approximate the ACOPF problem. You might not be perfect, but you might actually still be better than DC. And so that's maybe the other axis of comparison. Baosen, I know I cut you off. Sorry, I don't know if you wanted to finish the thought.
Yeah, so I was actually going to mention that point, is you can also always think sort of machine learning algorithms as proxies, right? So even for ACOPF, is a solver going to tell the optimal solution? Maybe, maybe not. Right, so always, a lot of ingenuity goes in designing this kind of solvers to know where you should start. For different systems, this could be very different. Whereas machine learning may make this step much easier. And then we'll, of course, run a solver to get the final solution.
Yeah, absolutely. Thank you. So maybe, yeah, we're a little over time, but if you have a moment, just a last question to close, which is, today we've talked about, a lot of different AI innovations, potential deployments that need to happen in power systems. What kinds of things do you need to happen on a meta level in terms of infrastructure, or community building, or knowledge exchange, and between whom to actually make some of these things happen?
Yeah, so maybe I can start because I think I can just reiterate the last point, which is accessible simulators, creation of tool and libraries. So I think that the need of creating a scientific community that is able to test their ideas, maybe even compete with new algorithms and really be able to understand what are the limits of this technology here would do wonders for it. So he has done wonders for many different communities. If you look at the planning community, the scheduling communities, they both build this type of infrastructure that are render their products very viable in industry. So I do think that this is an effort that it's really challenging. It's a lot of hard work, but a necessary one.
Yeah, just to echo that, I think, right. So the thing that's I think needed is infrastructure-wise, just a common set of problems, common set of data, common set of test benchmarks that we can use. We look at a lot of today's results, even from our group, as we're going to use benchmarks that were designed 30, 40 years ago. For example, power flow on some network that was not meant for this kind of problems, but we don't know better benchmarks, or we have preparatory data from our own networks, but that we cannot share. So I think having sort of larger set of common benchmarks, larger set of common data where we can all test our algorithms, I think that'll be very beneficial.
Yeah, absolutely. I think this combination of data, simulation environments, evaluation metrics that we all agree upon, I think becomes very important. Okay, so yeah, we're past time. So Baosen and Nando, thank you so much for a really interesting discussion and for sharing your perspectives on these topics. And for those who are still listening in the audience, we hope you continue to engage on these topics and build teams and actually work towards these things. So this webinar is co-organized by 4 different communities that are trying to do precisely that. So G-PST, ESIG, EPRI, and Climate Change AI. Again, the link to the Climate Change AI newsletter and the EPRI Environmental Grand Challenges newsletter in the chat. And I can also let the folks on the G-PST and ESIG side share those links as well if they'd like. But please do tune in and continue the conversation, and hopefully we can make some progress on these issues that were discussed today. So again, thanks so much, everyone, and have a good rest of the afternoon, evening, morning, wherever you are.
Thank you. Thanks for inviting.